today we're going off script a bit. We're leaving the textbook behind us. We're done with textbook material, and instead I'm going to talk about two papers. And these papers they're both 2018 at this point, but both interesting papers, and it is perhaps not surprising to you that I had some involvement in both the papers. And they're just kind of like a recap of where is mutation testing at right now, and what does the future for mutation testing maybe look like? So this first paper, the primary authors, Goran and Marco, they are Google researchers in Zurich, Switzerland. And this was mostly their work, and it was their presentation. And it's always a little awkward, presenting somebody else's presentation, but, I'll do my best. So how do we effectively test software? If we want to test software, we've got a program here on the left side. We want to get from a program to having a set of tests. And how do we do that? And that's basically what we've been talking about for most of the semester, right? How do we do that? Well, we can do that by some kind of test criteria. We can do it by node coverage or edge pair coverage or rack or any of the other things that we've talked about. So those are the things that we might use to fill in this blank, or we might use mutation testing. And any one of those solutions, we want to understand, what do we need to test? How do we need to build those tests? When do we need to stop? And how effective are the tests? And what did we miss? And each of these test criteria will tell us that in slightly different ways. So if we look at using mutation testing here, and again, as we talked about last week, we can use mutation testing for two purposes, and they're not exclusive, they're complementary. We can use mutation testing to develop a set of tests. That's what we're talking about here tonight, and that's what software developers tend to care about. We can also use mutation testing to assess the effectiveness of other kinds of testing. That's what researchers tend to use mutation testing for, but that's not what we're going to be talking about tonight. So we're going to be looking at using mutation testing to generate our tests. So generating mutants is cheap, right? In class these last 2 weeks, we have been doing it by hand. Doing it by hand is not cheap, right? You would not want to take 1,000 lines of code and 40 different mutation operators and come up with the 2 or 3 or 5 or 10,000 mutants that would generate. But doing it with a mutation testing tool that will automatically apply mutation operators to your code and automatically generate mutants, that's fast and easy. You can generate lots and lots of mutants, and you can do it very quickly. And executing the tests on those mutants is fairly cheap, depending on the number of tests you have and how many mutants you have. Still, we're relying on computer time and not human time. Not to make myself sound too old, but when I was in school and early in my career, right, undergraduate and early in my career, human time was cheap, computer time was expensive. You had a budget for the semester, and if you went over your runtime usage, you had to go beg to the department chair, to get more runtime usage so you could finish the semester. The exact opposite is true now. Extremely fast computing is super cheap, but all manual processes are super expensive by comparison. So creating those tests, that's the expensive part of testing. And so what do engineers care about? Engineers care about mutants that elicit effective tests, right? And I would even say that engineers care about effective tests. And maybe we can get engineers to care about mutants just long enough to get them their effective tests. But ultimately, software development engineers, they don't really care about mutants. They don't care that much about mutation testing. That's just a tool for them. And the more transparent the tool, the better, to get them from having a program to having effective tests. So this is an example of what the two Google authors were working on. They were actually building mutation testing into their I think it was GitHub pipeline that they were using in their development office in Zurich, Switzerland. And they were building a mutation testing system into there so that anytime a developer submitted a piece of code with changes, they would get back a message like this for every changed line. And so here, they would have submitted this run me function, and if A equals B or B equals 1, that would be a new line or a changed line. And their system would automatically come back as a result of that commit with the message back to the user. If you don't have any tests that would cause this mutant to fail, right? If we change this one line to A from A equals B to A not equals B, you don't have any tests that cause that to fail. You should think about adding a test case that would cause that to fail. So the process is really hiding mutation testing from the developer. Right? The developer doesn't need to know about mutation operators, and the developer doesn't need to know about what mutants subsume others. The developer only gets to see, if you had a defect in here that looked like this, you don't have a test that would catch that. Maybe you should write a test that would catch that kind of thing. And then the developer can do one of two things. The developer can say, yeah, I'm going to fix that. And then they'll get an opportunity to add a unit test into their unit test suite. Or they can say, no, that's a dumb thing. Why would I want to do that? That's not a mutant that helps me do anything useful. And they would click on the not useful. And then in the background, that data is being collected so that these two researchers can basically be working off of what their colleagues are doing, understanding which mutants are useful and which mutants their colleagues are telling them are not useful for writing new tests, so that they can fine-tune their mutation generator and continuously make it better as far as offering more and more useful mutants to their colleagues. So this was really cool because this avoids the whole thing we were talking about last week, and that I'll talk about in the next presentation about, this whole idea of, oh, well, we need to kill all the mutants, right? And it's like, that's an enormous amount of work, and what the heck is a mutant anyway, and why do I care? And this really avoids all that just by helping developers one little bit at a time improve their code just a little. So what's the status quo in mutation research? Generally speaking, the research community believes mutants that can be killed are good because they result in tests, and tests are good. That's what we want out of mutation testing. And equivalent mutants, those mutants that can't be killed, they're bad because they take up your time to figure out that they're equivalent, and in the end, you don't get any tests out of them anyway. What the Google researchers were proposing was that is really just too simplistic an idea. And there's a better classification than killable and equivalent mutants, and that's productive mutants and non-productive mutants. And they made the claim that killable mutants can be unproductive. I could kill that thing, but if it doesn't really give me a useful test, then it was just a waste of time. And an equivalent mutant can also be productive, and we'll come back to that in a minute. And that all of these non-productive mutants have a lot of costs associated with them.
Can you talk to Mommy about that?
So the problem at the moment is that this idea of what is a productive mutant, it's a very fuzzy idea. And at the time of this paper, we really only had a very soft answer, I guess I'll say, as to what is a productive mutant. Well, it's productive if it's killable and the test that results is effective. And it's productive if it's equivalent, but in the course of trying to understand it and trying to kill it, I realized something about my code that I didn't know before. Then even though I couldn't kill the mutant, I learned something about the code, and so it was still productive. So let's look at a couple of mutants here. So if we have our original, we're doing, this is a function to get the average of an array of floating point numbers. And so here inside the loop, we're summing them up. Sum equals sum plus the current element of that array. And we could change that excuse me, we could change that to be sum equals sum times the number in the array. So, you know, is this mutant killable? What do you think?
Yes, absolutely.
Killable, absolutely. Yeah, it sure is. This would not be hard to kill, right? Almost any test. You could probably craft a test that wouldn't kill it, but virtually any test would kill this. Fine, it's killable. Is it productive? What do you think? Can't quite decide. Sorry?
I guess I would argue no, because it's just a fairly obvious mutant. Like you said, pretty much any test would kill it.
Yeah.
So is it really
Yeah.
worth it? Probably not.
Yeah. Right. Good. So, but it is kind of a fuzzy answer, right? Okay, well, it's going to give me a test. Killing this would make me write a test. And if I didn't have any tests, then writing a test that would kill this would be better than having no tests at all. But considering almost any test would kill this, I'd probably rather have some other better mutant, whatever exactly that means, that would force me to do some particularly useful test instead of just throwing anything at it. So yeah, probably not productive. It doesn't break the algorithm in any kind of interesting way. It doesn't really force us to learn anything about the code. It doesn't really force me to come up with any particular sort of test. All right, so now I have another version of a similar program. Here we're doing get average. And so we're in this loop and we're changing average equals average plus the number divided by the length. And we're changing that to average equals average times the current number divided by the length. So this mutant is equivalent, but is it productive?
Yes, because the average variable isn't even used.
Yeah, exactly. So if I had this code to test and I got this mutant and I looked at this mutant and I'm like, okay, yep, I can kill that in a jiffy. Just about any test will kill that, just like the last one is what I'm thinking. And so I write a test and it passes. And I write another test and it passes. And I'm starting to think, am I doing something wrong here? And then eventually I realize, oh, average is a def without a use, right? And hey, isn't it nice we now have the terminology to speak about those kinds of things? I'm doing a def, there's no use. That's write-only memory. It's just, who cares what I do? I don't need that line of code at all. So now I understand something about my program that I didn't understand before. And to prevent somebody else from falling down that waste of time in the future, I'd probably just delete that line. So this is maybe harder. So I'm creating a new hash set here. And in the original program, I'm initializing the size of the hash set, which is something we can do in Java collections, right? We can tell it an initial size. And I'm initializing it to a times b. And in the mutant, I'm initializing the size of the hash set to a plus b. Can I kill this?
I don't think so, because it would double in size or something, right? If it reaches the capacity.
Yeah, this would be hard to kill because it's just going to take care of itself, right? If A is 10 and B is 10, for example, then the first hash set gets initialized to 100. And assuming I'm actually going to dump 100 things into it, in the mutant, it gets initialized to 20, but once I hit 20, it's just going to expand it anyway. So I might be able to kill this with some kind of a side channel attack. I might be able to kill this by doing a performance measurement, right? Because we could make the argument that strongly killing something, that I could strongly kill this mutant with a performance measurement if if the hash set initialization took long enough. But yeah, maybe I could kill it. And it's probably not productive unless the possible exception to that is if I look at this and say, oh, A times B, and now it's A plus B, and I can't kill this, but wait a minute, why is it A times B? That doesn't make any sense. So it could perhaps be productive if that happened to be an error, but you know, I don't know that that's very likely, so it's probably not productive. So it turns out relatively few mutants are productive, although that depends on what your definition of productive is. So, you know, if we say it's productive because it's killable and it elicits an effective test, that's nice, but we haven't really defined what an effective test is. And we can say it's productive if it's equivalent and it advances code knowledge. That's fine, but we haven't really defined what advances code knowledge means. But it's pretty clear that a lot of equivalent mutants are just dumb. And a lot of killable mutants don't require very much in the way of an interesting test. So, you know, the majority of mutants are probably not productive. And so if we could take those away and capture only the ones that were productive, then we'd be able to get an effective set of tests with less work along the way. So what's the cost of this? We actually did we actually did an empirical study here. We looked at 3 classes from Apache Commons, created a little over 3,000 mutants, found that there were about 661, about 20% were unkilled by the set of unit tests that were in this open source software. And so we took 2 goals here. Our first goal was to develop a mutation adequate test suite. In other words, kill all of the killable mutants. And then our second goal was to try to label all of the mutants as productive or unproductive. And again, our labeling is kind of fuzzy because we don't really have a good definition for what productive is. And what did we find? Well, we found that for these 3 classes, I'll just look at the totals line. We had 3,200 mutants. And the developer tests, the tests that the developers had written, which were not written using mutation testing, they were written using, you know, statement coverage or whatever those developers happened to do. We didn't analyze their existing tests, but about 20% of the mutants were left alive after the developers' tests. We then did some automated test generation with a tool called EvoSuite. EvoSuite basically does a static analysis of the code and tries to come up with test cases to kill mutants. It's not terribly effective, but it killed some more, and it took it took about 3 or 4% off it. And then we went through all of the remaining 544 by hand, and when I say we, that was actually me, because that's the fun kind of grunt work you get to do when you're a grad student. And actually cut that original number in half and got it down to just over 10% of equivalent mutants remaining. So when we looked at this, it was, looking at those 428 mutants was over 32 hours worth of effort. And we found in this case, about 33% were judged unproductive. And I think that if I had been using if I knew then what I knew now, let me put it that way, I would have used a stricter or narrower definition of productive. And I pretty much gave a very low bar. And if a mutant resulted in a test that looked like it could be reasonably useful, then I called it productive. I would probably turn the dial up now and say that a mutant is productive if it gives me a test that I'm not likely to get from some simple criterion like statement coverage. So I would expect that if I reanalyze this, I'd probably decide that more like half, or maybe more than half, of the mutants would be unproductive. And looking at these times, you know, you start to realize, okay, if I'm spending 32 hours for 400 mutants, you know, mutation adequacy, right? This idea of we're going to generate thousands of mutants and kill them all, that's just a ridiculous notion. So these took, to kill a mutant, took on average almost 9 minutes. To identify an equivalent mutant, took on average about 3.5 minutes. Now that's a heavily skewed number because most equivalent mutants are pretty much immediately identifiable as such once you have a little experience. You know, you can see things like return X++, and you go, okay, that plus plus, that's post increment on a return statement, that all gets thrown away, that's just equivalent. But there were others. I set myself a 30-minute limit. If I couldn't decide in 30 minutes that a mutant was equivalent, then I just called it equivalent and moved on. And quite a few mutants, you know, soaked up 30 minutes of time trying to figure out if they were equivalent or not. So these unproductive mutants, in general, they were a little faster than overall, right? They were a little easier to kill or a little easier to identify that they were equivalent. But still, we're talking, you know, 5 minutes per mutant for unproductive mutants. That's expensive. I mean, that's a lot of time spent. So what are some existing mutation selection strategies? I talked about this a little bit last week. The two general approaches are, we'll take a subset of mutation operators, that's selective mutation. Another approach is, we'll just randomly sample mutants. We'll just randomly take 5% of them or 10% of them. And existing, there's some interesting research that I was able to confirm that all of the existing selection strategies for mutants that have been around since, you know, the late 1970s, early 1980s, are no better than just selecting mutants at random, which is kind of disturbing because in any kind of science or an engineering thing, you'd like to think that you could come up with an algorithm that would give you better results than picking at random. It's remarkably hard in this case. So you're looking at the future for productive mutants. I'm actually going to talk a little bit more about this in the next presentation, so I won't spend a lot of time here, but basically, how can we better understand what makes a mutant a productive mutant? And then what kinds of techniques might we be able to use to predict whether a mutant will be productive or not, so that we have a higher probability of presenting the software developer with a mutant that will be productive and that will elicit an effective test. All right, so that's the summary of that one. Any questions or discussion here before we move on?
Just have a question
Sure.
related to the Google implementation of this seemed to be like, you know, a developer makes a commit and then some mutations are generated based off of that, like a little commit. But how do you actually approach like creating a corpus of mutants for like an existing code base, or like what do the tools do? Are they mostly like regex based, or?
So the internal implementation is actually a little unclear. I started writing a mutation tool. I did it in Eclipse, and Eclipse has a great ability. It's how Eclipse does its reformatting, and it's how it does its refactoring, all those tools. Eclipse basically gives you programmatic access to the abstract syntax tree for the code, and then allows you to manipulate the abstract syntax tree in various ways, which is, okay, perfect for doing mutations, right? So I could see that, oh, here's a statement, and this statement has an arithmetic operator in it, right? And then I've got this abstract syntax tree, and there's an operator, and then there's two operands, and so I can just replace that operator and then tell Eclipse, back that AST out to code and save that, and now change the AST again, back that AST out to code and save that. I don't know whether all whether all mutation tools work that way. I felt that it was highly effective. It was also a little slow compared to some other tools, but it's certainly an example of how you might be able to do that, because the AST, of course, has in it everything you need to know to be able to do statement deletion, right? At any point, you can just say, okay, from this node down, throw it away, and you've deleted a statement or part of a statement or a whole block. So it's got all the information you need. So I would venture to guess that most mutation tools are running against an abstract syntax tree representation of the code rather than against the source code itself, because that's just a lot more informative.
Yeah, makes sense. Thanks.
Sure. So, I haven't checked in with these guys since I think 2019. So it's been a couple more years now. I should check in with them and see how this is going, because they were basically doing their mutation generation by basically a hand-coded set of rules, and they were doing it kind of more like you were saying at first. I think they were doing it more on a one-shot basis by a regex, right? They'd take the diff and they'd run some processing against that line out of the diff to modify that code, which is a little bit of a different problem than throwing a whole program at it. But they were basically hand building those mutation operators and kind of hand modifying the rules as they were getting feedback about whether something was useful or not useful. My suspicion at the time was that probably wasn't sustainable, because that was probably just going to, quickly get into there's just way too many possibilities and way too many rules, and my rule set quickly gets too much to manage. And it starts to become an obvious application for some kind of machine learning, speaking of which, that's the topic of the second presentation. Right, anything else here? All right, so then let's look at our second presentation for tonight. All right, improving mutation testing with dominator mutants. This is actually an excerpt from my my PhD dissertation. I won't bore you with the whole thing. PhD dissertation was a crazy experience. I've got the new department, the new dean of the department in there, and I get like a third of the way through, and she stops me and says, "Why is your degree in information technology anyway? What does that have to do with anything?" And this discussion breaks out in the room between her and the faculty about the history of all the different degrees that are offered, and I'm standing in the front of the room going, okay, can we get on with, it was great, super fun. Just giving you all something to look forward to if you're in the PhD program. You'll enjoy that a lot. All right, so I'm going to start with a little story. Mutation testing in 2018. Here's Alice. Alice works at the Acme company, and if you're a Roadrunner fan, then yes, that Acme company. Alice is working on Acme's new product, the rocket-powered skateboard. And Alice is very concerned. She's writing the control software for the rocket-powered skateboard. And of course, the rocket-powered skateboard seems like an inherently dangerous thing. And she wants to test her software very thoroughly and is not sure what the best way is to do it. So Alice gets in touch with her friend Bob at GMU. Bob is no relation because, as you can see, Bob's got hair and this Bob doesn't. And Alice asks Bob, hey, what's the best way for me to test this software? How should I make sure that this is okay? And Bob says, oh, you should use mutation testing. That's great. And Alice says, mutation testing? Never heard of it. Tell me about it. And so Bob explains, right? You take your original program and you put it through some mutation engine, some mutation tool like the Mutomatic 18. And that tool uses mutation operators like relational operator replacement to create a mutant, or literal variable replacement, or arithmetic operator insertion, or some other set of mutation operators. And it'll generate a big set of mutants, and each of those mutants will have some small difference from the original. And then you try to write a test that will pass on the original, but will fail on the mutant. And so, for example, we can take this first mutant, and then we looked at this example last week, I'm pretty sure. And if we made a test that said assert that max of 2 and 1 equals 2, that would pass on the original, it would fail on this mutant. Great, so we've killed that mutant. Now it turns out that when we write a test to kill a particular mutant, we also tend to kill a number of other mutants with the same test, which is nice, right? May as well get them out of the way early. So Alice seems to think, yeah, that sounds like a pretty good idea. I understand how that works. This will be fun. So she takes her, very small control program of only about 2,000 lines of code, and she sticks it into the Mutatic 18, and the Mutatic 18 spits out something like 20,000 mutants. And Alice is sort of immediately taken aback by the number of mutants that she has to deal with. But okay, she won't quit yet. She'll take a look at it first. So she picks a mutant, and she writes her first test. And she runs that test against all of the mutants. And she finds that she's killed about 45% of all the mutants with her first one test. And this is pretty exciting. She says, oh, these 20,000 mutants, they're not so bad after all. This isn't going to take too long. I just killed almost half of them with my first test. She writes a second test. Now she's killed about 65% of the mutants. She writes a third test. She's killed about 75% of the mutants. Curve looks like it's dropping a little, but the results are still good. Let's keep going. And then she finds this mutant. We talked about this one last week too. And replaces if I is greater than J, replaces it with if I is greater than or equal to J. And try as she might, she can't figure out a way to kill this mutant. Anything she does, it passes on the original, it passes on the mutant. Eventually she gives up, throws that one aside. Now she's done 4 units of work, right? She's written 3 tests and she's evaluated 1 mutant. So she's done kind of 4 chunks of work. Didn't make any progress with that last one. And then she'll, take on a few more and find a few more that are equivalent that she can't kill. And she's starting to get a little concerned with the shape of this curve, because as she continues to do more work, she's killing fewer and fewer mutants with each additional test. And then she finds she gets into this long string of equivalent mutants. And she's doing work and she's making no progress at all, and she's just kind of filling up her basket with things that she's throwing away. And now she's starting to feel like it's pretty clear I'm asymptotically approaching something, and I'm not even sure it's 100. What's going on here? So she gets back in touch with Bob. Hey, Bob, what's the deal? I'm seeing this. This is disturbing. What's going on? Bob says, oh yeah, those are equivalent mutants. You can't kill those. Don't worry about them. You just have to look at them and set them aside. It's not that big a deal. And Alice says, well, how many of them are there? Bob says, oh, usually about 10 to 20%. And Alice is thinking, 10 to 20% of 20,000 mutants? So I need to look at 2,000 to 4,000 mutants by hand, one at a time? That doesn't seem like such a good idea. And so Alice's Mutatic 18 goes in the back of the trash pickup. Alice goes back to statement coverage because she knows how to do that. She knows that she's going to actually get finished, right? She knows that she'll be able to complete the job that way, which was not at all clear in mutation testing. And that's the end of the story for mutation testing in 2018. And that's kind of a typical end of the story for mutation testing in development practice in 2018 and in 2021 for that matter. So what went wrong? Alice ran into 2 major problems. She ran into equivalent mutants, right? And as we know from last week, those are syntactically different, but semantically identical to the original program. No matter what you do, you can't kill it with a test. You have to evaluate it one by one. And unlike with a test, where when you write a test, you're probably going to kill more than 1 mutant. With an equivalent mutant, you're going to spend your time analyzing it, but that analysis isn't good for any other mutant. It's really you just get to take that one off your plate. So it's very inefficient, requires very unrealistic amounts of work, just like we saw from the Google researchers. Alice also ran into redundant mutants. And a mutant is redundant if it's always killed when some other mutant is killed. And it turns out that the vast majority of mutants that aren't equivalent are also redundant. And the effect here is that it inflates the mutation score and it obscures progress. And this is exactly what Alice saw when she started. She wrote her first test, she killed 45% of the mutants because most of those mutants were redundant. And when she wrote another test, and she got up to 65% because most of those mutants were redundant. As you get further up that curve, and we've got a question in the chat, is the level of efforts to kill a mutant typically logarithmic? The answer is kind of yeah, because as you get further up that curve, there are fewer and fewer redundant mutants to kill because you've progressively killed more and more of them. And you're left with the smaller number of non-redundant ones, but you are increasingly killing them one at a time instead of killing 40% of them at once. And so this redundancy inflates your mutation score, right? Alice was thrown off by, I wrote one test, I'm at 45%, yay, this is great. She was actually not at 45% of her work, right? She had barely scratched the surface of her work. So this inflation gave her a misperception about how far along she was in her testing. And so that leads us to the idea of mutant subsumption. So just like we've been talking about all year, where we have test criterion that can subsume each other, mutants can also subsume each other. And so one mutant subsumes another if there's some possible test that kills the first mutant, right? The first mutant is a killable mutant. And every test that kills the first mutant also kills the second mutant. If that is true, then the first mutant subsumes the second mutant. Now, informally, what does that look like? So if we had this in gray, this universe of all the possible tests we could write, and then in blue is all of the tests that kill the second mutant, and in green is all of the tests that kill the first mutant, MI. Then MI in green subsumes MJ in blue because any test that kills MI also kills MJ. That means MJ is a redundant mutant. Now, in theory, we would look at it in terms of all possible tests. In practice, we are incapable of writing all possible tests. And so instead, we have some sprinkling of specific tests across the domain of all possible tests. And we use that to approximate this subsumption relationship. And we see here from these specific tests that are represented by the little red marks that, yes, okay, there are 3 tests that kill MI, and all of those tests kill MJ. And then there are also some other tests that kill MJ. So based on this set of tests, we propose that MI subsumes MJ. We can use this information to build up a subsumption graph. This is just like the graphs that we've been looking at for our test criteria. So when we run our tests across our mutants, so here in this example, we have 6 mutants, we have 5 tests. Let's run those tests. And here on this chart, a green circle means the test passed, a red stop sign means the test failed for that mutant. And now we can use this data to build up the relationship or an approximation of the relationship between our mutants. And we end up with this graph. And what does this graph tell us? This graph first tells us that M3 and M2 and M5, those are what we call our dominator mutants. These are non-redundant mutants. But there are redundant mutants beneath them that they subsume. So if I'm able to kill M2 or M5, and I can kill M3, then I will have killed everything that they subsume as well. And if we look at a specific case here, let's look at M3. M3 is killed by only test 2, right? This is the column of tests that kills M3. M3 is killed by test 2. M3 subsumes M1 because M1 is killed by test 1 and test 2. So as long as I can kill M3 with test 2, I've killed M1. M4 is killed by test 1, test 2, test 3, and test 4. So M1 subsumes M4 and M3 subsumes both of them. I also have a live mutant, M6. M6 wasn't killed by any of these tests. Is M6 equivalent? Anybody want to take a shot at it?
I mean,
It's
we
kind of
can't
a trick.
tell. We can't tell just based on the graph. We'd have to,
Yeah.
like you said, look at it manually and essentially figure it out.
Yeah, exactly. It's kind of a trick question, right? The answer is, I don't know. These 5 tests didn't kill it. Maybe I could write one that would. Maybe I can't. I don't know yet. But M6 doesn't appear in the graph because it doesn't subsume anything and nothing subsumes it. So it's kind of off to the side in its own place. And then M2 and M5 are indistinguished mutants. They have exactly the same behavior. They're killed by exactly the same test. Now let me clarify that a little bit. I said exactly the same behavior. That isn't really what I meant. What I meant is they're killed by exactly the same tests. They might not return the same result, right? But they both fail the test. So M2 is killed by test 1 and test 4. M5 is killed by test 1 and test 4. So they fall into the same node on this graph because they have exactly the same behavior with respect to these tests. Now maybe I could add another test that would kill M5 but wouldn't kill M2, and then M2, this would split and M2 would become its own node that subsumes M5. But with this test, with this set of tests, I don't know that yet. So what I'd like to do, ideally, I'd like to have some mechanism to find mutants like M3 and like M2 and M5 so that I could present those to the developers and get rid of these, especially M4 that's killed by almost everything, right? Get rid of these that are subsumed and don't distract my developers with that, right? Because those are redundant mutants. So historically, I said we talked about this last week, but actually, I'm not sure that we actually did talk about that this last week. Historically, there have been 2 general approaches to trying to take this problem of, wow, there are just way too many mutants to deal with, and try to turn it into a more reasonable number of mutants. And the first is variations on selective mutation. And selective mutation was actually Jeff Offit's PhD dissertation. And in selective mutation, what we're trying to do is we're trying to identify the best mutation operators. And what do we mean by best mutation operators? Well, the definition of best has varied over time. But we're trying to find mutation operators that generate good tests and don't generate a lot of equivalent mutants. And so we'll identify those mutation operators and we'll use those and we'll get rid of others that don't. Right, so we'll just take other mutation operators and now we're not going to use them. We're not going to generate any mutants with them. We're just going to generate mutants with these operators that we've decided are good ones. And the other approach is to slice it the other way, typically by random mutant selection. And there's a lot of research out there that's been done to select at random some number of mutants, and 5% is a typical number, 10% is another common number. So we're going to slice this the other way across all of the mutation operators. We're just going to randomly select some small number. And there's variations on this that try to balance it across mutation operators or balance it different ways. But in essence, we're doing random selection of what's out there, hoping that we get enough good ones that it'll work out okay for us. So part of my research was to look at those different approaches to mutant selection and see how well they worked. So I took a look at 4 small programs that are well known in the literature, a little too well known in the literature. They've been around for a long time. They're kind of considered no longer all that useful because they're a fairly small size. But I looked at those 4 programs and generated mutants for them using a number of different approaches. And First, I'll say that all of the gold dots that you see here, this gold area is actually made up of tens of thousands of dots. Those tens of thousands of dots are every combination of 1 or 2 or 3 or 4 mutation operators from a particular tool for C that generates tons of mutation operators. So these are all the possible combinations. The green dots are the combinations that scored the best. And what do I mean by scored the best? What I mean is that they're closest to the top left of this graph, where as we go up the graph, we're killing more and more dominator mutants with our tests. And as we go to the left on the graph, we're doing less and less work. So anything that's on the leading edge, the leading top left edge, is an optimum solution for having killed the most dominator mutants for that amount of work. And then when we look back at historical approaches, we see that the traditional approach to selective mutation is this diamond or this triangle, and it's kind of middle of the pack. And the typical selections of random selection of 5 or 10 or 15 or 20 or even 25% of mutants, they're also kind of middle of the pack. And statement deletion, which was proposed a few years ago as kind of the magic solution that does really well and doesn't take too much effort. Well, it doesn't take too much effort, but it's also middle of the pack. For any one program of these 4, we can find solutions that are up here in the red area, right? So for a particular program, we can find a good selection of operators, but for all programs together, all 4 programs together, we can't. And even though this is only 4 programs and they're not very complex programs, if we can't find a good set of mutation operators for 4 simple programs, we certainly can't find a good set of mutation operators for programs in general. Right, so we'd like to be up here, and we can't get there by random selection, and we can't get there by selectively choosing which mutation operators we want to use. So there's some related work that has this great quote: "There's surprisingly little room for improvement over random sampling," which is kind of astonishing and disappointing, right? We're in a science and engineering field, and you're telling me that I can't do better than just pick mutants randomly. That's an astonishing and worrying statement, but there's a lot of research to support it. So how can we get better? And the final part of my dissertation research was, well, what about using machine learning? Can we use machine learning to get better than random selection? And so for those of you who are not really familiar with it, let's do a quick review. What is machine learning and how might we use it? So I was using a particular technique called supervised learning. And in supervised learning, what we do is we have a training set of data. And the training set is a set of features and a matching set of labels. And features are some kind of measurable characteristic. So let's say that we want to have a classifier, a supervised learning classifier, and we want a classifier that can tell apart dogs and cats. And so what features might we give it? Well, we might give it eye color and ear shape and coat color and coat length and the size of the nose relative to the face and the length of the leg relative to the body. Those are things we might measure, and those are features. And then we would label those features with what their outputs are. And in this case, for our example, we'd label them as, okay, this set of features represents a cat, and this set of features represents a dog, and that set of features represents a cat, and that set of features represents a dog. And we're going to feed all those things into the classifier, and the classifier is going to, I'll just say magically, right, to black box. We don't know what's going on in there. It could be a decision tree, a neural net, lots of different things could be happening in there, complex math, we don't care. It's going to magically learn from that training set that we give it. Now, this training set, as shown, is like 3 things. No, we're giving it tens of thousands of examples. And then we're going to have a test set, and we're going to use the test set to evaluate how the classifier did. And the test set is going to have features and labels too. And these features and labels are the exact same schema as the training set, but different data than the training set. So it's still eye color and ear shape and coat color and coat length and nose size and leg length, and it's still dog or cat, but it's not the same, it's not the exact same data that we used in the training set. Then we're going to feed the test set features into the machine learning classifier. And the machine learning classifier is going to give us back a set of predicted labels. And then we're going to compare the predicted labels with the actual labels and basically grade how well the machine learning classifier did. So what's this going to look like for us? So let's take a set of features. Here's a set of features. Now, this is a picture. I am not suggesting that we're feeding images into this classifier. There are classifiers that take on images, right? There are classifiers that will take in images and try to recognize images. It's a popular thing to do with classifiers. That's not what I mean here. I'm using this picture as kind of a shorthand to mean coat color and ear size and all those other things we talked about. So I'm going to feed that into the machine learning classifier. And then I'm going to take a dog and a cat and more dogs and more cats, and I'm going to have all this different data, and I'm going to feed that all into the machine learning classifier. And now, presumably, the classifier is trained. And now I'm going to take a feature. I'm going to take a feature from my test set. I'm going to feed it into the classifier. The classifier is going to say, oh, I'm 94% confident that's cat and 6% confident it's dog. And we say, yep, that was a cat, so good. You're right on that one. Then I'll pass in this set of features, and it says 93% dog. Good, it's right again. Pass in another one, 98% dog. Pass in another one, 97% cat. Pass in this last one, the classifier comes back and says, I'm 54% sure that it was a cat. Well, this one was actually a dog. So what went wrong? Maybe we didn't give our machine learning classifier a big enough training set. Maybe the training set didn't contain dogs that have quite this set of features. Or possibly this dog just kind of looks like a cat, and it's perhaps an understandable, an explainable error on the machine learning classifier's part. So great. We can see how that works. That seems like it might be useful. Now I need a set of features. Where am I going to get a set of features from to describe a mutant? And we came up with a set of features. So we came up with a set of features that included the mutation operator. Is this an arithmetic operator replacement? Is it relational operator replacement? Is it something else? What is the operator that's being used? And then what's the specific mutation that's being made? Are we taking, for example, an arithmetic operator replacement of something plus something and changing it to something times something? Or are we doing something else, right? What's the exact change that we're making? If we look at the abstract syntax tree, where are we? Where are we making this change? Are we making it in an if statement, in a while statement, in an assignment, in a return statement? Where are we in the context of the program? And how did we get here? What's the abstract syntax tree's parent? Am I in a while statement that's inside an if statement? Or am I in a return statement that's inside a for statement? What is the path of how we got here? And what am I operating on? Am I operating on a literal or a variable or some operator or some function call, right? What are my operands? We took all that information and gathered it for over 100,000 mutants, if I remember correctly. And then we tried to label them as best we could, whether they're equivalent, whether they're trivial, whether they're dominator mutants, they're at the top of the graph, and what their dominator strength is, by which I just mean, where are they on the graph, right? 0 would be the bottom of the graph, 1 would be at the top of the graph, and some intermediate number would be in between. And an AST is the abstract syntax tree. So that's the data structure that the compiler will create as a representation of the source code. And then we went to predict our utility. So we put all that information into our machine learning classifier, and we got out data that we represented in curves like this. This is a ROC curve, a receiver operating characteristic curve. This graph itself has an interesting history. It comes out of World War II research into early radar systems. But here it means a specific thing to us. On the y-axis, we have the true positive rate, right? The number of times that I said it's a dog and it was a dog. And on the x-axis, we have the false positive rate. The number of times I said that it was a dog, but it was a cat, or vice versa. So the y-axis is the things we got right. The x-axis is the things we got wrong. And what we want to see is a curve that comes as close to this upper left area as possible. If I guessed right every time, I'd make a correct guess and a correct guess and a correct guess, and my curve would go vertically up as I continue to make correct guesses until I've made all of my correct guesses and we're done. If I were to make random guesses, okay, I made a guess, I had a 50-50 chance of being right, and I continue to make random guesses, and I'm following this gray dotted line right up the middle. So the further I get towards the corner and away from the gray dotted line, the better off my guesses are. And so this black line, black solid line, indicates how well we were able to predict equivalence. And particularly, specifically, it means that I could identify 25% of my equivalent mutants, the ones I was most sure were equivalent. The 25% that I was most sure were equivalent, I was right with only getting 3.5% of them wrong. So I was overwhelmingly right. And I could identify the 50% of equivalent mutants that I was most confident in while only getting 16% wrong. Now, the further we go, the less confident I am and the more often we're wrong. But that initial guess, where I have high confidence, we're actually doing pretty well. And now we can judge this, right? We can sum this all up. We can integrate the area under the curve to get a score for how well we've done. So we integrate that and we have 0.736. Now, if I were perfect, the integrated area would be 1.0. If I was random, the integrated area would be 0.5. If I was worse than 0.5, that means I actually have an inverse predictor, and I should take whatever it said and I should just reverse it, and then I'll be back on the right side of the curve again. So here's how we did. For equivalence, we were able to pretty well predict whether a mutant was equivalent. And we were able to pretty well predict whether a mutant was trivial. But our ability to predict whether a mutant was a dominator was basically no better than random. All right, I'm going to skip a little faster through these things. We basically wanted to judge how well are we doing. And so if we took one particular class, and this particular class was the one with the median results, so it's an entirely unremarkable example. If I had perfect knowledge, this is kind of going back to the graph that Alice was looking at, where work is on the x-axis, right? As I do work by either writing a test or looking at a mutant, I'm going down the x-axis. And as I kill dominator mutants, I'm going up the y-axis. If I had perfect knowledge, I would have this black line. I'm basically killing one or more than one dominator mutant with every test. And so it would take me 150 or 160 units of effort to be complete. If I picked mutants at random, then I'd be this red line. And I'd be, making some progress, and that progress sort of falls off until eventually I had to do 550 units worth of work in order to finally kill all the dominator mutants. And with our machine learning approach, we were able to do this blue line, which is kind of halfway, or maybe not quite halfway, between random and the best I could possibly do. So it's certainly a significant improvement over random, even though it's not great. Not important. We're going to skip that. The other thing that I get here, which is interesting, is I get, for the first time in mutation testing, I get an output that I could use for knowing when to stop. Because this small blue line that goes the other way, this downward blue line, this is the line of what my predicted utility is. Remember, just like with the cats and dogs, we were saying 98% dog, 90% cat. Oh, 49 or 51% cat. I'm not really sure about that one. We get the same thing with mutants. So here, these first mutants, we're 80% sure that that's an equivalent mutant. And so we'll pick that best one first, of course, right? Why start with junk? We'll start with our best guess. And we kind of rapidly come down from 80 into the 70s and the 60s. And by the time we get to our 50-50 point, where we're 50% sure this is an equivalent mutant, we've actually accomplished most of the work. So we can use that prediction of how good the mutant is. We can use that as a stopping point. And we have some inference about how far done we really are. We're about 90% done when we get to the point where we're 50% confident on our predictions. And that relationship held over lots of classes that we looked at. All right, so last of all, Alice and Bob get back together. What should mutation testing look like in 2020? This was written in 2018, and I was very, very optimistic. Now I'm thinking maybe it's more like, what should mutation testing look like in 2030? So what should it look like? Well, we like a tool just like we have now to generate a bunch of mutants. We'd like to take those mutants and we'd like to run static analysis against them and automatically generate some tests to kill some of them and to start to understand what their subsumption relationship might be. That was an aspect of my research that I didn't talk about here tonight. That's going to give us some tests. It's going to give us sort of the starting point of a subsumption graph between the mutants. Then we'd like to execute those tests. We'd like to kill mutants. We'd like to find what the real subsumption is based on that, based on those automatically generated tests. And we can do that pretty cheap, right? May as well automatically generate tests and run them and see what we can kill, because it's fairly cheap and easy, at least from a person's time perspective. And they tend to kill a whole lot of them. So then we'll remove the redundant tests, right? Because we can find that, oh, this test kills more than that test does, and everything that's killed by that one is also killed by that one. So we've got redundant tests. Let's get rid of them. Tests are expensive to maintain. Let's get the smallest set of useful tests we can. Then let's take the rest of the mutants and let's run them through machine learning and predict their utility. And then we can iteratively, like in the Google case, say to the developer, hey, here's the most useful, what I predict to be the most useful remaining test. You should write or the most useful remaining mutant. You should write a test to kill this. And when they've done that, you can say, okay, now I estimate that you're 60% of the way done. Do you want to continue? Here's the next most useful mutant. Great, you're 70% of the way done. Do you want to continue? And we can continue to use that Google approach of giving developers at any time the most useful mutant that we can predict. And then that kind of brings us to this flow chart, which is really actually very similar to the flow chart that I talked about last week, so don't need to spend a lot of time here. But basically, we're going to add in this machine learning classifier to try to predict high utility, productive mutants to give to the engineer. So some ideas for future research. Most modern tools are using selective mutation. They've already downscaled all their mutation operators to the ones that they think are best. There's an older tool out there for C called Proteum. Proteum has a ton of mutation operators, and some of them are really wacky. But sometimes those mutation operators produce really good mutants. So we should take those from that kind of obsolete tool and integrate those mutation operators into a modern tool to see if we can get higher utility mutants. We should look at better ways to extract context, right? We were looking at the abstract syntax tree. We were trying to figure out some things out of the abstract syntax tree. There's more information in there, right? Maybe we look at def use information. Maybe we can figure out other things to look at. But how can we improve the context? And then how can we use better classifiers? When I did this, I was mostly using decision trees and really kind of elementary neural nets. But in the last couple of years, there's been an explosion in neural net research and in being able to run neural nets on graphical processing units, right, on GPUs. TensorFlow, for example, runs on GPUs, super fast, super powerful. So we could probably throw better classifiers at the problem, and maybe we could do better. And I'm actually working with a group of undergraduate researchers at Virginia Tech who will be doing exactly that this summer, trying to figure out whether they can throw some better classifiers at the problem and get better results. So if you're in your PhD program and you are looking for a research topic and you like working with Paul Ammann or Jeff Offit, there's a lot of room here in mutation testing. It's a hot topic. There's a lot of papers still coming out. I am living proof that this is, PhD worthy research effort or research work. You can definitely get your degree on this. If you're in a master's program, but you've chosen a master's program with a research aspect to it, again, this might make a good research area for you. There's a lot to do here. So, that's it. The one other thing I'll mention is that as part of this research, one of the really fun parts of this research is that I got to work with a lot of interesting people around the world, and there will be some familiar faces on here. Right? We've got Paul Ammann, Jeff Offit, Dr. Rangwala is on here. A researcher in Brazil that I was working with, a master's student in Boston, a researcher in University of Washington, my Google friends in Zurich, statistics professor in Turkey, and then my daughter, who at the time was an undergraduate student at George Mason, actually contributed to some of this work as well. So that was really fun and really rewarding to work with people kind of around the world on this. And
I actually know Marriott. I didn't know she was your daughter.
Oh yeah, you know her.
Yeah, she's
That's
really
okay.
good to work with.
You don't have to say anything about her.
No, she's wonderful. She's great to work with.
Yeah, she was fun. She came up with a couple of really good ideas that we talk about it. I was doing this work. She was undergrad. We'd get together like one night a week on campus for dinner and talk about what I was doing. And she had a couple of really breakthrough ideas that were like, oh, that's a great idea. Let me try it. And I also got to go to cool places. My favorite conference was in Graz, Austria. That was amazing. I also had to go to Cleveland, which, I apologize if you're from Cleveland or otherwise love Cleveland. I didn't find much going on in Cleveland. But Seattle, Chicago, lots of fun conferences. So it was a really good time. All right, so we'll call it there. We're 6:15. So let's take a 10-minute break. We'll start back up at 6:26. We'll have a little bit of brief discussion on this presentation if you're interested, and then we'll go into our work groups for today. All right, so see you in 10 minutes, 6:26.